so this is the section on annuities due. Now, you say, well, what the heck is annuities due, and what difference does it make to my world? Well, the fact of the matter is that annuities due are used a lot in leasing. Okay? Leasing. And all an annuity due, what we mean by an annuity due, it uses the idea of making a payment at the very beginning of the period. The basic thing is with an annuity due is that the payment is made at the beginning of the period. So on the very first day of the loan or the very first day of the lease, the very first day you make that first payment. That's a little different than what we looked at before, because what we looked at before, you were making a payment at the end of the period. So let's say, for example, you had a loan for 1 year. There was 12 payments to be made. You made the first payment at the end of the first month, end of the second month, end of the third month, and so on. That's a traditional loan, okay, where you make the payment at the end of the first period. In a lease, it's different, or in a annuity due, it's different. You make the first payment up front. Now, there's two types of annuity due, as we've seen. There's two types of annuity. There's also two types of annuity due. The first one that we talk about is the simple annuity due, and the simple annuity due is the same as the simple annuity, it's just a due. And the trick is with that is that the stream of payments, okay, is made at the beginning of the payment interval, and the payment interval and the compound frequency are the same, which is what we said for a regular simple annuity. You know, that if it's, for example, the payment is monthly and the compounding is monthly, okay? So this is the same type of setup that we saw with a simple annuity. The only difference is in a simple annuity due is that that very first payment is made straight away. And because the very first payment is made straight away, what we need to do is to adjust the formula a little bit. And here's the adjusted formula. The formula that we've used all along is this part right here. The annuity due just adds on this little bit. So this 1 plus I. So we're multiplying it by 1 plus the periodic interest rate. That's the only difference to the formula. The hardest part in an annuity due is identifying the fact that it's an annuity due. And you'll see it's an annuity due by definition when you look at the annuity, when you look at the problem, and the problem says the first payment is made immediately. Something as simple as that. The only difference in the mechanics of the formula is that little add-on that goes on the back, which is 1 plus I. Okay, so 1 plus the interest rate. Now, if we had, that's the future value formula, and the future value formula is when we're trying to figure out what it is at some point in time. The present value formula is what we do when it comes back the other way. So we're trying to figure out what was the value in the past. So the present value formula, and the present value formula is the exact same as it was for an annuity, but it has this 1 plus I on it. So that's the only difference in the formulas is this 1 plus I added to it. Let's just look at a simple problem here, okay? To the nearest dollar, how much will Stan accumulate in his RRSP by age 60 if he makes semi-annual contributions starting off at $2,000 starting on his 27th birthday? Assume the RRSP earns 8% compounded semi-annually, and that no contribution is made on his 60th birthday. So effectively, we look at this and we say to ourselves, well, what do we got going on here? Well, he's 27 years old and he's going to make a $2,000 contribution on that day. Well, that would mean that that would be an annuity due because it's the payments made right at the beginning of the annuity, okay? And it's $2,000, 27th birthday, and it's going to stretch him until he's 60. So what's that, 33 years? 33 years. So This is a payment that's going to stretch on for 33 years. Next thing we need to look at is assume the RSP earns 8% compounded and semi-annually, and that he's going to make payments semi-annually. So we see a couple of common things here: semi-annual contribution and semi-annual compounding. The two semi-annuals, the payment and the compounding, would indicate that it's a simple annuity. The fact that it's paid at the beginning of the period means it's an annuity due. So this, by definition, is a simple annuity due. The mechanics of calculating it are exactly the same, save for that little bit on the end. So, for example, the payment is $2,000. The interest here, it says is 8% compounded semi-annually. So we got to divide that by 2 in order to get the periodic interest rate, which turns out to be 4%. And the total number of periods, well, there's 33 years, 2 payments a year. 33 times 2 is 66 payments. We substitute all this into the formula, and here is the formula. And notice this is the tag on that goes on an annuity due, this 1 plus I. So we basically throw the information into the formula. The payment is $2,000. The interest I is 4%. The N is 66 minus 1 over the periodic interest rate. And because it's an annuity due, it's multiplied by 1 plus I, which is 1.04. We do all the math on that, and we get $640,156. So effectively, over 33 years, earning that interest rate, it will accumulate to $640,000.
We also have general annuity due. Now, keep in mind, we learned last time that the general annuity is really looking at an annuity in which the payment interval and the compounding frequency are different. Okay, so we need to be able to define what exactly is a general annuity. So we're looking for that different payment interval and different compounding frequency. Now, from the perspective of an annuity due, the payment stream is really related to it being at the beginning of the period. The payment's made at the beginning of the period. So it's important that we understand a general annuity due when we see one. As we've seen before, when we looked at general annuities, the calculation is a little more complicated. We first need to calculate or recalculate the interest per period. Okay, in order to do that, we need to calculate C, which is the number of compounds per year divided by the number of payments per year, and then we take that C into a formula to calculate I2, which is the revised version of the interest per period, and that's 1 plus I to the power of C minus 1. So all we got to do from a due situation, like I said before, is we're doing the exact same formula, but with the 1 plus I2 attached to it. So that would indicate an annuity due.
If we look at this one here, this next example that you'll find in your book, repeat example 12.1 with the change that the RSP earns 8% compounded annually instead of 8% compounded semi-annually. Okay, so here we've got a situation where the 8% is compounded annually. Okay, so this is the difference here. We're changing that. So the compounding period is annually, and the payment is semi-annually. Okay, so if we look at it, the payment is one type of payment stream, and the compounding is another type of stream. This is by definition a general annuity. Okay, so in order to be able to define from a simple annuity to a general annuity, the two are different. In this particular instance, then they'd be different. The fact that the payment is made at the beginning of the period says that it's a due. So it's by definition a general annuity due. We just do the calculation on it. I is 8%. The interest is only compounded once, so it's 8%. Periodic interest rate. We got to calculate this version of C because it's a general annuity. The first thing we need to do is number of compounds per year divided by the number of payments per year. That's 1/2, which is 0.5. That C then is plugged in to calculate the I2. So 1 plus I to the power of C. We do the math on that, and that comes up to 0.039, on and on. So we take that information, we plug it into the formula, and again, the I2 is calculated right here. We plug that in to the power of 66 minus 1. This little add-on is here because it's an annuity due. We do the math on that, and it comes to 618,606. So you notice that it's almost the same, 640, 618, but it just shows you the power of the compounding. There's less compounding in this particular problem. It's only done annually, so it's a smaller amount at the end. Power of compound interest demonstrated.